interest of some of us in cosmology and to this present day. So I'll start my talk by asking a question. What if the force driving the acceleration and expansion of the universe isn't constant but evolving? And what if we're able to detect this evolution with subtle correlation between the cosmological background temperature fluctuation and the hot gas and galaxy cluster? For several years we have assumed that the dark energy behaves like the Einstein cosmological constant, unchanging over time, until recently when there is a question mark on that. And so we want to say a little part of this story by investigating into this using the observed cross correlation between the ISW and the TSZ. Okay, and outline we need to give a short introduction and the theoretical framework and talk about the data we use and the result that we have presently. Like we know that the dark energy puzzle has intensified dramatically following the DESI result, the baryon acoustic oscillation measurement showing tension with different data set. And in the WA/W0 plane, we see that this is not actually a result that is due to some random fluctuations or systematic issues, but they are signal consistently pointing to dynamical dark energy. And the question is, this naturally motivates us to explore alternatives beyond our landesidia. And in the landscape of dynamical dark energy, we have different sort of models. We have the scalar field models, the modifier of gravity model. But for this work, we are interested in the Quintessence, which follows the scalar field with canonical kinetic energy and rich dynamics. And so in the Quintessence dynamics, we have three subclasses which are interested in the Thawing, the tracker, and the scaling freezing. And here I show the comparison of the density of matter, radiation, and the potential. For Thawing dynamics, initially behaves like cosmological constant and then begins to evolve recently. But the tracker has a frozen period in the past and then tracks the background expansion. But the scaling freezing has like two parts. The first part, which describes some complex scaling evolution, and then followed by slow phase. Our foundation for the theoretical framework starts with using minimally coupled canonical scalar field with the about Einstein expression here, and then the term here is the kinetic part with metric signature, and also the potential, and also capture the action of matter and radiation for completeness. And so if we vary the action with respect to metrics, you arrive at the Einstein field equation, which of course obeys the Klein-Gordon expression. And in the FLRW cosmology, we can write down the modified Freeman expression, and the term here, the second term here, sounds like a friction driving this whole expression to a slower phase. So it drives the field to a slower phase. And from the kinetic part, you can have the kinetic reduced to the first term here. Here I just write the expression for the energy density and pressure, where the pressure can be negative if the potential dominates over the kinetic part. And putting this together, we have the equation of state. And because the potential for different Quintessence dynamics is different, so that influences what you get with W5. And for the dynamics we use under the Quintessence, we assume different form of potential that is able to mimic their behavior for numerical stability. So we have the exponential potential for Thawing, inverse action like potential for tracker dynamics, and double exponential for the scaling freezing. It's double because of the two parts. The first part follows the scaling behavior, and the second part follows the freezing part. And on that is super horizon and quastatic approximation. You can write down this expression, and in this case, the growth factor will be different and modified for the Quintessence. And then if we write down the evolution of the sigma 8, which all goes in as recipe to the matter power spectrum, and so which is a combination of primordial amplitude normalization, the growth factor, and the transfer function, which sets the turnover in the matter power spectrum, and that is connected to the physics of the matter radiation equality. Having all of this together as theoretical background, we can then move to how we model the all of this connect together with the angular power spectrum. We particularly focus here, we're focusing on the Hilo model, on the large scale gas bias model, because we are sensitive, our data is sensitive to the large scale. And so, following this expression of the gas density fluctuation, which is proportional to the matter density fluctuation, and the product with gas bias, which is inversely proportional to the redshift, we can write down the electron density fluctuation, which all goes into the expression for the Compton Y, which is an integral over the electron density and temperature log line of psi. And we can break this down in this expression and make some proper conversion between the proper length and the comoving distance. And then we can factor out the WXZ, which captures the product of these three parameters, and then we can just use that as a free parameter because it captures the astrophysics of the TSZ effect. Now go to the ISW temperature fluctuation, delta T over T, and from the Poisson equation, which relates to the gravitational potential, we can calculate the potential, the gravitational potential, which takes as input D of Z and delta M. And so because the D of Z and these factors are different for different models, so we obtain, that means the gravitational potential is sensitive to the different kind of quintessence model adopted. And all of these goes in eventually as recipe into the angular power spectrum. For the TSZ angular power spectrum, is an integral over the matter power spectrum weighted by the SZ canal. And we factor in the contamination, the residual contamination in the Y map due to CIB, radio point source, and infrared sources, and add that to the calculated power spectrum to be able to recover the observed power spectrum, which we measure from the maps. The same way with the TT, which TT here is the ISW, actually. So the ISW power spectrum is weighted by the ISW canal, and then the product of the ISW canal and the SZ canal with the matter power spectrum would under linear approximation, we can calculate the cross correlation angular power spectrum. And looking at the data, I decided to take this plot from Professor Jankpe Jie's talk in the 21 centimeter summer school with his permission. He gave a beautiful talk on cosmology. And then I fell in love with this plot so much, and it basically tells me these two effects. The CMB photons coming from the edge of the visible universe encounters the hot gas galaxy clusters, and then we see this due to the inverse country scattering. And the same for the ISW, CMB photons enter into time evolving gravitational potential well, and then because of the decay of the gravitational potential well due to dark energy, the photons climb out of the well with the net energy, and we see this as the ISW effect. And these two, the cross correlation between the TSZ and the ISW characterizes the largest scale perturbation in the universe, and therefore they are correlated on large scale and can even be sensitive to the gas on large scale. And we made the cross correlation detection reported in our paper in 2014. If you look at this plot here, we show the SZ-ISW cross correlation as a black line against 100 simulations. And the right plot here is showing the signal to noise ratio of this 100 simulation against the dotted black line, which is the signal to noise ratio of the genuine ISW cross correlation. And under no correlation hypothesis, the true data deviate from the simulated one, thank you, sir, by 3.6 sigma. And yes, here we show the angular power spectrum and the matter power spectrum, the ratio of the dynamical matter power spectrum and the matter power spectrum of the different dynamics for different redshifts. And the major path spectrum and the calculated angular path spectrum is what we show to the right, and DL is, we multiply the prefactor with the CL already. And we capture the systematics due to CI being a cross correlation by cross correlating the ISW map with the Planck, 3 Planck frequency dependent map, and realize that they have the same spectral dependence, and take their average weighted by the free parameter to quantify the systematics linking into the cross correlation. And the result is that we realize that for all the parameter in the space, the parameter distribution, we realize that the constraint on our parameter, both astrophysical and the cosmological parameter, be consistent about 2 sigma, and it depends. You may not look at that as a tension or as it were. And to appreciate the contours, the estimate of the cosmological parameter, we decide to just show what we have here for visualization's sake, and then calculate or derive the estimate on the baryon to matter ratio. And we could see that the Thawing has the highest compared to other model included in the city. And here I'm just showing a radial plot to compare the performance of the model against 5 metrics. And the field region is just the normalized value of the metrics, and the normalization ensures that you have, all the values are between 0 and 1, and the smaller radial distance indicates better performance. Of course, we see that which is the blue is close to the center. All right, so here we show the model parameters from the different intensities dynamics model, and see that the prefers in lambda that is not 0, and that is and the scaling freezing have some mild deviation from standard expectation, which indicate that this small deviation leaves their imprint in the observable ISW-tSZ cross correlation. And because the ISW is sensitive to the decay of the gravitational potential, we can calculate the ISW strength from each of these models, but we can test this unless we have high precision ISW data set, which probably will get a picture from Euclid and maybe LSST. And so here we show the ISW strength calculated from the understanding of the gravitational potential, for which the different dynamical dark energy is sensitive to, including Landesidian, and see that the scaling freezing has the highest strength. And so our future outlook will be to probably involve some time varying equation of state analysis, and might be also useful to look into multi-probe synergies, where you combine the ISW so that it's set to be able to obtain a better understanding of the dark energy evolution. Whether it's Einstein is still an open question. Thank you.
I was wondering on the field that you are using, like, do you include any dynamic impacts, like on the concentration or on different parameters? And did you, like, how much did you test your Euler model compared to other one or simulation?
All right, so we didn't include any baryonic feedback, if I get the question right. You need to probe up to small scales to be able to do that, because the ISW has an angular resolution of 160, so it means that structures beyond 200 in the multiple space is smeared out, and so you cannot really test baryonic effect with this. We focus again on the last scale.
So how does your TSC ISW cross compare to the CMB Galaxy ISW?
Oh, thank you for that question. That's also good. I think that the ISW Galaxy cross correlation is quite established already. So looking at the ISW-tSZ is looking at some other. It was before, but you wouldn't find. So the reason is because of the ISW effect on large scale is dominated by cosmic variance, so the amount of mode extractable is limited. Right. So we are probably looking up to high resolution measurement of the ISW in the future, and then more cross correlation of this kind of ISW-tSZ will be
higher than the Planck team's ISW.
So this is from Planck, yes. Planck
yeah, but I mean the TSZ.
The map I showed.
Yeah, yeah. All right. So that.
This.
So
both are actually Planck.
So you have considered 3 different quintessence models, and I guess each model has at least 3 parameters.
Yes.
Okay. And I wonder what kind of parameter sets you're choosing, because depending on the parameters you choose, they can have very different impact on the observational quantities.
Yeah.
Are they already reasonably constrained by other observations?
Yeah, most of the guys, the theory guys, usually you see them constrain this kind of dynamics using a combination of supernova data and probably BAO and some other data set. But using the cross correlation, the observable cross correlation data set, I haven't found much work constraining this with the cross correlation data set. I mean, the Thawing, the Quintessence pathways dynamics. Yes, it has 3 parameters which are sensitive to the formalities of the model, and these are model parameters that are also included in this analysis I'm treated for. I'm sorry if it's not showing too. I mean, here. So for the overlap region, here is the CDM with the different models, and also for Thawing, for example, we have 2 other model parameters. Here we have 2 and we have 4. Here, which are sensitive to formalization and formalism of the models. I'm not sure if I get the question where I.
Okay, so let's start with speaker again.